Waalaikumsalam doktor, and good morning.
Jam attendance 58, tapi baru 52. Ada yang sharing screen dah? Ada yang sharing Teams nih online? Jangan apa tuh? Share link attendance. It's okay. Lambat sedikit. Terus tunggu tadi. Orang cancel. For now, we continue for chapter 3, which is measurement of pressure. So for our tutorial last week, we need a class replacement because we don't have tutorial last weekend. So I think I will set the tutorial with you later. Nantilah kita buat undian di WhatsApp group. So di lecture note boleh download, you can download it in ITEL. Tapi belum tiada jawapan tutorial lah. So you need to focus lah during class for the answer for the jawapan tutorial, for the exercise and examples. So I'll continue with the chapter 3, measurement of pressure. So the cause outcomes is the ability to distinguish different types of fluids, fluid basic properties, and apply theory and application of various fluid statics properties, including measurement of pressure and solving hydrostatic forces. So in this chapter, we'll focus on the measurement of pressure. So this is the outline, which is first top topic is learn about the pressure, and then pressure and forces, and then what is the measurement device used to measure the pressure. The first subtopic is pressure. So in this lecture, we'll discuss about the pressure applied in a fluid at the rest, and then we'll calculate pressure using various kind of manometers. So this is we'll do some exercises and examples for to calculate the pressure. So pressure can be defined as a normal force exerted by fluid per unit area. So as you can see, this is the sample of object which have an area and exerted force. So it is a force applied on a unit area. We call it as pressure. So this is the equation, which is pressure equals to force over area. And same equation 3.1 show the equation force over area. So the unit for force is Newton. We also can use the kilonewton over area. So as you can see, this figure illustrated the pressure force acted perpendicular to enclosing surface. So this is our force, and then the pressure inside the syringe. For example, it is a syringe. So the pressure is here. So this is the example of pressure for a solid surface for this one for human. So it same force perpendicular to the surface unit area. So it will produce a pressure. So I'm not focusing more on the solid surface lah, because we focusing on the fluid. So for fluid at a rest obey hydrostatic equilibrium, where its pressure increase with depth to balance its weight. So what we learned before, fluid has a density, and different type of fluid at different density, different value of density. So as you can see here, pressure equals to atmospheric pressure plus density times gravity times height, PGH. So this is pressure. Atmospheric pressure is here, P. And then for the pressure, P naught plus PGH. PGH ni the density of fluid times gravity times height. At the surface of fluid, the pressure is an atmospheric pressure. Sinilah yang the surface. Kalau di laut, di atas air tuh, the surface, it is called atmospheric pressure. So weight of the liquid pushes against wall of the container, producing a pressure. I mean, for example, of this container. So as we go deeper, the pressure will increase. Macam kalau mandi air kolam kah ataupun di laut, makin kita turun berenang ataupun diving, for example, as you go deeper, when you go diving, the pressure di telinga terasakan makin tinggi pressure dia. So makin dalam makin tinggi pressure kalau di dalam air. Kalau hiking kan naik gunung, itu makin kita ke atas makin tinggi pressure. Kalau liquid makin ke dalam makin tinggi pressure. So how for the pressure exerted by gas, in a closed container, gas molecules exert a force when they collide with each other and with container walls. Ini ada gas, for example, we have gas molecules inside the containers, and we use the vacuum pump keluar itu semua, exerted all the gas, remove the pressure reduced to zero. So it is called as absolute zero pressure or absolute vacuum, because there are no molecules or gases inside the container. So we can use the barometer to measure atmospheric pressure. So because we use it barometer, so it also can be called as barometric pressure, atmospheric pressure on the surface. So as altitude increase, atmospheric pressure decrease. So this is the example of barometer. We have can be measured using two reference, which is first one is gauge pressure and absolute pressure gauge. It's different. So I will show a video next to show the example of these two different type of pressure measurement. So this first one is the gauge pressure, which the atmospheric pressure as a reference, because its major pressure is how much more than the atmospheric pressure. And then for the absolute pressure gauge, why it is called as absolute pressure gauge, because of the absolute zero of absolute vacuum pressure is used as a reference. You can see this.
Consider a normal pressure gauge. Before connecting the pressure gauge to any process, the reading in the gauge shows 0 psi. As we had discussed earlier, every object on Earth will undergo an atmospheric pressure, but that atmospheric pressure is not indicated in this gauge. That is because this pressure gauge is designed to indicate the measured pressure is how much more than the atmospheric pressure. That is, here the atmospheric pressure is taken as the reference standard. Now let's connect this pressure gauge to a container filled with liquid. The pressure gauge will indicate the pressure exerted by the liquid in the container. This pressure is known as gauge pressure. The atmospheric pressure varies from place to place depending upon the altitude of the location and prevailing weather conditions. When atmospheric pressure varies, precise measurement can be achieved only if a fixed unchanging reference point is established. So here, absolute zero pressure is used as the reference. Absolute zero pressure is the pressure of a perfect vacuum. The measured pressure in which absolute zero pressure is used as the reference is known as absolute pressure. Consider that we need to measure the pressure of air in a tire. If we use a pressure gauge, the gauge will indicate the pressure of air inside the tire only, which is the gauge pressure. If we use an absolute pressure gauge, then this gauge will indicate the sum of pressure inside the tire and the atmospheric pressure. That is, absolute pressure is equal to gauge pressure plus atmospheric pressure.
So To be summarized from the video, we have two types of pressure, as I mentioned earlier, which is absolute pressure and gauge pressure. So what is the difference? The absolute pressure is actual pressure at a given position or sum of the pressure due to a fluid and pressure due to atmosphere. And gauge pressure is the difference between absolute pressure and atmospheric pressure. So as you can see, so from the equation, absolute pressure equals to gauge pressure plus atmospheric pressure. So for example, macam yang tayar tadi lah, tayar kereta. Kalau yang pump kereta tu, itu gauge pressure sahaja. We didn't include, tidak termasuk di atmospheric pressure. Yeah, difference with the gauge pressure. Gauge pressure, dia tolak saja lah ni, absolute minus atmospheric. So you can see this illustration. Absolute gauge and vacuum pressure are related to by each other. So you can see this from this figure. Gauge pressure is here. So the absolute pressure is the summation of gauge and atmospheric pressure. And for the vacuum, this one, atmospheric minus with the atmospheric minus with the absolute goes to vacuum. So this is the other illustration. The atmospheric pressure equals to absolute plus vacuum. And yes. Okay, it's almost similar on this one. So we next we continue with the example. So example 3.1, show a vacuum gauge connected to a chamber reads 40 kilopascal at a location where the atmospheric pressure is 100 kilopascal. So determine the absolute pressure in the chamber. So the given information is the vacuum, which is 40 kilopascal, and then atmospheric pressure is 100. So we need to determine the absolute pressure. So P vacuum equals to atmospheric minus absolute. This one kan tadi sini. Atmospheric minus absolute. So we need to find the absolute pressure in the chamber. So absolute equals to atmospheric minus vacuum. So 100 minus 40, the absolute is 60 kilopascal. So that one is direct question. Ini example 3.2, a bit tricky. So a fish is currently located at a depth of 10 meters in the ocean. So the atmospheric pressure for the sea level is 103 kilopascal with a density of 1025 kilogram per meter cube. So what is the gauge pressure at this point? And second question is, what is the absolute pressure? Okay, I can give you 5 minutes to try to do it. Yeah. So the given information is the height, h is 10 meter, then atmospheric sea level is 101.3 kilopascal, density also given. So you need to find since the pressure at the surface, which is P naught, is atmospheric pressure, so we can solve the gauge pressure. Yeah, so okay, I think I'll give 5 minutes for you to do this example. So later I'll mention anyone names to give me the answer. Yeah. Oops. Okay. Anyone get the answer for A? Gauge pressure. Panggil nih nama siapa-siapa, random. Azrin Azahari. Ada?
Ada, dokter.
Okay. Did you get the answer for A? Dapat berapa?
100.55 kilopascal.
100.55. Okay. Okay, thank you. Nanti tunjuk jawaban. Betulkah tidak? Okay. So for the second question, perempuan lagi lah. Sophia. Ada, Sophia. Sophia, you're not here?
Ya dokter, kejap dokter.
Tengah mengira. Okay, it's okay. Kira dulu. So we show the answer for A. So the first answer is correct lah. So how to find P gauge equals to density PGH, density times gravity times height. So just substitute the value, insert the value here. Make sure your unit is correct. And you have 100 kilopascal. So you correct lah jawaban tadi. So question untuk B, determine the absolute pressure is atmospheric plus inilah 100 tadi. Dapat sudah, Sofia? Berapa? Belum, tengah mengira. Pun Sofia next question nanti. Next. Anis lah dulu. Anis Suhaiza. Dapat jawaban for B? Adakah Anis? Anis. Pun belum kira.
Yes, dokter.
Yeah, what is your answer for B? Ini. Dapat berapa B?
201.9.
201.9. Okay, thank you. Siapa tadi? Anis. Sophia ready ya nanti next question. Okay.
Oke dokter.
Okay, thank you. So the answer is 201 and 3 kilopascal. Okay, betul lah kamu jawab. So next subtopic is pressure and force. So pressure and force, the pressure are equal distributed in all direction when force is applied, which is equal pressure lah. So Pascal principle, which is also called as Pascal law in fluid, which is gas or liquid mechanics, states that fluid at rest in a closed container, a pressure change in one part is transmitted without loss to every portion of the fluid and to walls of the container. Maksudnya, pressure sama aja lah yang di dalam nih. So pressure exerted at one surface, mana di sini A1 is equal to pressure exerted on any other surface A2. So this allow allows a small force applied to a small area to be converted to a large force applied to a large area. So pressure dia sama di sini. Yang berbeza adalah force. Example, this one, the original force F1 equals to P1 times A1. Inilah small area. Lepas tu yang bila ada large area, force dia increase. Tapi pressure masih sama. So second force ni 10 times the original force. And then next example is pressure variation with elevation. Kalau tadi correlation with the area and force. Force dia makin besar lah bila area tu membesar juga kan. This one elevation. So point at the same level below the surface area at all the same pressure regardless the shape. Maksudnya semua depth kedalaman yang sama, the pressure-nya sama sahaja. Di sini. Yang penting di kawasan yang sama lah with the same fluid yang sama. So kalau however as we go deeper, makin masuk ke dalam air, pressure dia increase. Tapi position di ketinggian yang sama adalah having the same pressure. Okay. So this is the pressure variation with elevation. Kita tengok sini lah. Same theory dia. Because as we go deeper, makin ke dalam air, as you go deeper, the pressure is higher. Tengok yang ni container ataupun you can use botol air. Di sini yang paling tinggi kurang pressure. Yang paling bawah container ni kalau untuk lubang pressure-nya makin tinggi sini lah. That's why ni jarak tu yang paling jauh. So ni example P1 dengan P2 pressure di sini and pressure here. I think in this one you can try to do it in nantilah example supaya lebih senang. So from the figure, sum of all forces must be zero and forces acting are first force due to the pressure 1 on the surface area acting up. F1 equals to P1 times A1 area of the cylinder. And then first to the pressure P2 on surface area A2 acting down. Ini tadi acting upwards. And then P2 acting downwards. P equals to pressure 2 equals to pressure times area 2. So force due to weight of elements of fluid. Weight kan W equals to mg. So that's why F equals to mg. Kalau yang biasa punya F equals to ma. Tapi bila ada gravity here, di sini, so it's convert to mass times gravity. Also can be convert to PGA H, density times gravity times area, and then the height difference biasa. Inilah untuk mengkira force due to weight elements. So this one, so finally we can get P1 equals to pressure here is equals to P2 plus PGH. The pressure yang sini. Next, pressure at the same level. Yang tadi different level kan pressure, which is pressure at P1 and pressure P2. So it's different height. So in this one, with the same height, pressure with the same height, so pressure at any point at the same level in body of fluid at rest will be the same. So we consider the horizontal element of fluid, the cylinder with cross-section area in fluid density, pressure PL at the left hand end and pressure at the right hand. And sama lah, pressure PL and pressure on the right. So force equals to PA. So yang di sini equals to pressure here. Ini senang sikit lah. Because as long it's have the same height ataupun depth, the force is same. Pressure dia sama. So this concept applied even though there is no direct horizontal path between points, provided that the points are in the condition body of fluid. So it is still true for two connected tags with which appear to have any direct connection. So ini pun sama. So P equals to Q, R equals to S. Ini sama juga lah, walaupun bentuk dia begini, tapi dia punya pressure still same di antara with having the same height ataupun depth. PP, pressure at P equals to pressure at Q, pressure at R equals to pressure at S. So kalau yang sini pressure R equals to P plus PGH. Z tu H lah dia punya height. Ini R. Kalau S ni pula, the pressure at S equals to pressure at Q plus PGH. Ini sana. Jarak ini. Okay, so we try to do some exercises. Two submarines are under the sea surface doing their daily job. So the seawater has specific gravity of 1.025. So submarine A and B ada dua lah, submarine A and B. For the submarine A is 200 meter and submarine B 5 meter above the seabed. So as detected by the sensor, pressure of seawater acting on submarine A is 5030 kilopascal. Ini pressure dekat sini lah, PA yang tulis. So if the seabed is horizontal, calculate the pressure acting on submarine B. So mau kira pressure di sini berapa. So given specific gravity, given 1.025, and then pressure at A pun ada. And then specific gravity equals to density of fluid over density of water. Sebab dia bagi specific gravity. So to calculate the pressure, PGH tadi kan formula dia. So you need to find the density lah. Yeah. Okay. Boleh try kira dulu lah. 10 minutes. Sampai 9:06. Banyak lagi masa. Okay. Boleh try to do it. Okay, paling dapat jawaban. You type di chat na. Did you get the answer? So, density pressure at B. Berapa? Okay, Zul. Oh, Sophia. Baru 2 orang. Yang lain tidak. Okay, Zul, Sophia, Joseph, Aisha dengan Muhammad Syafiq. So all get the almost the same answer, right? So now let's see the solution. So first we need to find the specific gravity because dia hanya bagi di given specific gravity dengan pressure. But we need to find the density of fluid. Inilah. Cari the density of fluid. Ini seawater lah tadi. So then the specific gravity given and also density of water 1000. So you get 1025 density of fluid. So next, carilah the height at A. Height at A because transfer at A equals to density AGH kan. So that's why dia jadi inilah. This one. So just masuk substitute the value density at A given and then over density times gravity. And you get 500.24. Tadi lah, dari sini. 24 meter. Lepas tu, cari height at B. Height at B. Ini lah. Sorry. So we need to find height at B equals to outside 200. This one 200 plus HA 500. Lepas tu minus with 5 dapatlah HB. Get height at B is 695 and 24. Next, we need to calculate D. Pressure at B, PGH. Density times gravity times height at B. So 1025, ini density tadi, times with gravity times height dekat B. 695, and then get the answer 6099. So itulah yang dapat tadi. Siapa yang 6,990. Okay lah. So semua okay. All the answer can be accepted. Betul lah semua. Okay. So next we continue. With the pressure measurement device. So the device can be used to measure the pressure is barometer. So this is the barometer. Ini saya nampaklah kalau mau check pressure. So you can see previously density pressure equals to atmospheric pressure plus PGH, density times gravity times height. So ini the basic barometer. Ini saya punya pressure lah, check pressure. Barometer, and this is the barometer. So as we learn from the previous lecture, kalau tengok shape of the fluid, dia punya meniscus, kalau mercury supposed to be dia U shape lah. Dia begini. Terbalik. Set semuanya. U terbalik. Kalau fluid, the meniscus untuk U lah. So ini apa? Is the vacuum. And then the surface of water is atmospheric pressure. W equals to mg, which is also PGHA. You can try to do the exercise later, so you can see the videos.
Aristotle famously said, "Years of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, but his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher. But the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
So the video should be the application actually study in how the parameter works. So this is the other example. Yang kanan ni air ini burden pressure. So on the left is the burden pressure gauge. So to measure pressure of fluid in the pipes. So ini lah burden pressure. Burden pressure gauge. Ini supaya boleh tengok berapa pressure di dalam pressure air dalam pipe ni. So we continue with the next example. So which is example 3.3, which is to determine the atmospheric pressure at a location with the barometric reading is, find the atmospheric pressure. The location with the barometric reading is, how is something? 740 mmHg, and the gravitational acceleration is 9.805. So assume the temperature of mercury to be 10 degrees Celsius, where the density is 13,570 kilogram per meter cube. So kita mau cari the atmospheric pressure lah. This one, 5 minutes, 9:30. I give you until 9:30 to calculate, to do this example. Okay. Ini for this example, this one I call panggil siapa-siapa lah untuk jawab, untuk bagi jawaban. So kita mencari atmospheric pressure berapa. And this is the information given. Barometric reading given is 740. Ini from the barometric reading, you can get the height lah. Okay, paling pojok. Sana. Kini Joshua. Ada. Ya.
Ada dokter.
Dapat berapa? Atmospheric pressure.
98.4 kilopascal.
Okay. Okay, thank you. Betul. Okay, just updated lah value dia. 15, density, gravity, 9, so height 0.74. Don't forget to change the unit, convert the unit. You know, unit conversion supaya dapat Pascal. 98.46 kilopascal. Okay, good. So next, manometer. Tadi barometer. So now manometer. Manometer are used to measure pressure in pipes and other closed vessels. Yeah, sample of manometer. So I think ini nanti you will do it during your hydraulic lab. I think in year three, you will see this instrument in your hydraulic lab. This one to calculating the pressure using manometer. So now for the closed, closed vessel. So this is an example of simple manometer and then differential manometer. So I think you can try to read this one. Gitu. The bottom section. So this one you can try to do it during your tutorial and example later. So what can be summarized from here? You know, for each arrow, mark plus or negative signs. Kalau plus, for arrow whose direction are towards the point where the pressure is to determine. And then for the negative, direction are leaving the reference point. So this one, thing to simplify, senang time buat ano lah. You can try to just read it later. Untuk senang paham, I think we can try to do some exercises. So for example, in this one, sample manometer, point A, di sini lah, the pipe A is the reference point. So untuk PA, untuk to calculate pressure at A, so arrow 3, starting here lah, 3 plus arrow 2, ini kalau ikut dari sini lah, open end, plus existing pressure. Ya, ini ada negatif nih. So dia turun, ini air tuh sini. Negatif sih sebab dia jauh turun. And then yang ini P at B ini dia equals. Jadi tiada lah. Yang ini sudah turun, lepas itu dia kasih seimbang. Bila dia turun sini, and then naik balik. Jadi cancel lah kan. Yeah, this one negative, and then this one positive. So in this one can be cancelled. That's why tidak kira. And then arrow 2 naik, and then arrow 1 pun naik. Need going down. And then existing pressure, sebab di sini open end, as you can see, at open end, bila ada open end, it is ada atmospheric pressure lah. That's why negative. Negative PA ni PGH lah. Y ni D height. Okay. So kenapa zero? The atmospheric pressure zero because manometer N zero pressure. So manometer N is open to atmospheric pressure. So atmospheric pressure is zero untuk kode manometer. Cari video lah dulu.
Measured by manometers. The simplest manometer consists of a graduated U-shaped glass tube closed at one end and connected to the gas container at the other end. The tube is filled with liquid mercury. When there is normal atmospheric pressure inside the container, air pushes a column of mercury up to a height of 760 millimeters of mercury. At this height, the pressure exerted by the mercury column balances the pressure exerted by the air. As air is removed from the container, the air pressure is reduced, and the column of mercury drops down. You can read the pressure as the difference between the mercury levels in the two arms. If the container is evacuated completely, the columns of mercury will reach the same height in both arms. Any other liquid can be used in a manometer. However, the height of the manometer depends on the density of the manometric liquid. Water is more than 13 times less dense than mercury. Therefore, the water-filled manometer would need a height of about 10 meters. The use of such a manometer would be rather awkward. Manometers for measuring atmospheric pressure, called barometers, do not contain a liquid. Inside a barometer, there is a small, evacuated metal capsule. Changes of atmospheric pressure make the capsule expand or contract. These tiny movements are transformed by springs and levers to the indicating arm, which points to the actual value of the atmospheric pressure.
This one quotation. This is the example of measuring pressure with manometer. This is the example untuk manometer. Kalau barometer tadi, simple kan? Yang this one, manometer is used to measure the pressure of a gas in a tank. So the fluid uses a specific gravity of 0.83 and the manometer column height is 55 centimeter. So if the local atmospheric pressure is 96 kilopascal, determine the absolute pressure within the tank. So we need to find, pressure dalam ni. Pressure dalam ni, P itu. This one give you, boleh try buat dulu. Give you 5 minutes. Is it enough? Yeah, try to do it in 5 minutes. So this is the last example for today. Okay, try to do it first. Until 9:45. And specific gravity given. Height pun ada. Atmospheric, ada 6. This one, don't forget to change it to meter. Parang oops. Okay. But P equals to berapa? Can type your answer in the chat section. Irisa, 100. Zul pun dapat 100 kilopascal. Okay, good. So most of you get almost the same answer. So Sophia, Setcheri, Nurin, Robin, Melanie, Raina, Ivan, Mika, Aminullah, Sam, Ilman, Arif, Aisha, Jesse, Joseph, Izatu, Overawida. Okay, so since of most of you, I think all of you get the same answer, 100.6, 100.858 kilopascal. So inilah. Yeah, the answer is correct. So first, kena cari lah the density of fluid is 850 kilogram per meter cube. Ini this one absolute pressure equals to atmospheric pressure plus PGH. Atmospheric given 96 kilopascal. Itu typo tidak K lah sudah ada exponent 3. 96 exponent 3 P Pascal plus density 850 times gravity times height 0.55. Ini conversion unit. So you get 100.6 kilopascal. Okay, good. All get these correct answer. On this one, exercise 3.2. You can try to do it. Boleh try buat lah. This one, so a bit complicated. So, kang babanyakan. So, ni boleh nanti try buat. To calculate the pressure at point A. Here lah. So, kalau water, nanti di sini. You can try to do it. Dia punya jawapan, jawapannya 585.6 kilopascal. Kalau cari pressure dekat A, to find pressure here. Lepas tu, pada A ni lah. Patutnya di sini naik, tapi this one cancel sebab dia akan sekali dengan yang ni kan. So, nak cari yang di sini. Yang cancel. Ini untuk cancel. Ini pun dah payah. This one pun cancel. Yang ni sebab yang di sini naik, dan di sini turun, naik, dan naik. This one positive. Tapi ini dah boleh cari. Because this one kena cancel oleh sini. This one pun cancel yang sini. Ini pun dah perlu. Yang perlu this one. Okay. Yang perlu cari ini. Ini pun dah perlu. Oh, yang this one perlu. Sebab dah dapat cancel because yang di sini ni liquid yang berbeza. This one water, lain. Ya, ini yang kita kalau water. Water, this one, dia nak bagi tahu fluid apa, but it's mentioned, yang ni adalah specific gravity dia, 13 point, macam tak keluar pula di situ. Ini contengan. Pasti kau nak kira sini, cakap tidak tersambung pula pattern saya. I think problem masalah lain kan. It's okay. Sama sini lah perlu dicari. Okay, sudah balik. So, sama sini lah perlu dicari. Ini dia turun negatif, this one positif, maupun positif. Nanti boleh saya cari lah. Mencari pressure in the pipe PA itu berapa. I'll try buat. Okay, I think that's the jalan. That's all for today. I think that's all for today. Jalan. Thank you everyone. So boleh try buat sendiri exercise 3.2. Okay, for
Alright, Doctor.
For the tutorial hari Kamis, I will do it online sebab I involve with the exhibition, ada pameran di Labuan, fakulti hantar. Hari Rabu saya jalan, jadi kelas tutorial we do it online, so combine sajalah, because online kan combine jam 10 from 10 to 11. Okay, so we'll discuss tutorial 1. So tutorial 1 belum discuss lagi. And then for lecture next week secara face to face lah, okay? Macam lama nak jumpa. Kalau tidak air lagi boleh try tadah lah awal. Okay. Okay, thank you everyone.
Thank you, doctor. Thank you, doctor.
Thank you, Doctor.
Thank you. Tutorial chapter 3 I will upload lah nanti dekat ITEL.
Thank you, Doctor.
Thank you, doctor.
Okay, Doctor. Thank you, Doctor.
Okay, Doctor.
Thank you, doctor.
Thank you.